So how are you? I guess some of you may notice my sound has changed a little bit because I was quite sick over the weekend. But I think I'm surviving, so not dying. I mean, still alive. It's not COVID, so don't worry about that. I mean, I almost recover. Maybe a 95% recover. But I guess it's not. Just shouldn't affect our teaching. Um, just a gentle reminder that the homework is due on Thursday, midnight. So please submit your answers, and then if you are late, then you would deduct points from that. I think beyond that, we will just only allow 1 day delay, but other than that, probably got 0 from that. Since we don't have many midterms, so please submit your assignment on time. Okay, I mean, we don't have quiz, we don't have thing. The assignment is a thing that keep you learning. Otherwise, if you don't, it's a math, right? So if you don't really work on that, then you don't really understand. So make sure that you submit your homework. And we also have quiz, but the quiz 4 will be released soon. I mean, I have a TA checking the answers, but I would pretty soon release them as well. So very quickly whoa, what happened? Very quickly that we are reviewing the sampling distribution and go to estimation. Okay, I just spent 5 minutes, less than 5 minutes for that, right? So this is the starting point of collecting data and how data related to probability, right? So far, topic 1, we talk about data, calculate mean, median, mode, variance, correlation, this kind of stuff. And in topic 2 and 3, we actually talk about probability, random variable, right? And after that, we talk about this sampling distribution, and then we focus on one important thing is called the sample mean, right? We want to know what sample mean looks like under simple random sample. And under simple random sample, we know that the sample mean of the sample mean with the population mean and variance of the sample mean will be proportional to the population variance, but inversely proportional to the sample size. And law of large number tell you that when the sample size get super large, you will exactly get the population mean. And the central limit theorem said when you have large sample, the sample mean will looks like a bell shape. Okay. And after that, we talk about last class is the central limit theorem is very useful, but you have to rely on the population variance. Sometimes you have a good guess, sometimes you don't. Right? You may ask what's a good time, If you do product control, you do have a good variance of that, right? It's how precise the machine is doing. Actually, you do have variance. There's some way you can estimate variance, come from your engineering idea. So it's not completely no use for the central limit theorem. There's some way you can estimate variance. But in many cases, you don't know. So we have to rely on other assumptions, right? And what we need to assume the underlying population follow normal, right? The bell curve is behind. And after that, we know we can use the T distribution to describe the sample mean, right? So that is the main key of the this, right? This is the one that we'll be using this class. Is this guy, right? This guy is something we'll keep using. Okay. This is the one. Okay, this is super important. And also what we know is the when we have binary data, which is 0, 1, and here we can also simplify with the standard error is connected to the mean because in binary data, which is with non-linear distribution, the mean and the variance are related. So this is something that we don't rely on T. So that is a good thing. So I hope that you will see Why we don't need central limit theorem? Because central limit apply, but this is if you notice, this is a binomial distribution related, right? Because sum of all the things divided by n, right? So it's just like a binomial, but you divide by n. Okay? So but that means that everything goes very smoothly. Okay. So without further technicalities, then we will go to estimation. Okay. Estimation. As we said, why we need estimate, because that is the main goal, right, of the data, right? You want the data to estimate some model, right? The model will help us to deliver prediction and do whatever we want to, right? The short GPT, right? They train the model. Train the model is to estimate some parameter, or almost all, I would say, statistical analysis is based on estimation, right? It's estimating something, and the model will be useful for certain purpose. So estimation is the, I guess, a key of most of the analysis there. Okay, and things we're interested in is often much more simple. It's also mean and the variance, population mean, population variance, and of course you're also interested in other things, kurtosis, skewness, whatever you're interested in. But mean and variance is the most common thing, at least in our class. If you want more, then you would be beyond the scope of our class. And estimator is the way to estimate, okay, the parameter. So it's a function of the sample. So if you recall, this guy is called statistics, right? This definition. And if you use the statistics to estimate something, that's called estimator. If you remember, statistics is a random variable, so estimator is also random variable. So there's nothing new there, but just saying that estimator is the way that the method we use to guess, say, population mean, right? Before you have this, before you get a rule, get an algorithm, before you collect the data, right? You have figured out that what should be the rule before you collect data, right? And this rule apply to every single data, right? And once the data realized, you apply this rule, you get a number. And the number you got is called estimate. Okay, estimate is a rule, and estimate is the number you get. Okay, estimate is the particular realized one. Okay, so it's a number. So it's that once you have the data, it's no longer a random variable. Okay, so you have to distinguish what is estimate and estimator. Okay, so that is something that I want you to know, because this is often emphasized in textbook. Although I don't see why that is very important, but who would confuse? But anyway, just let you know, there's some estimate and estimator. And here would be two main types of estimator. One is called point estimate, right? So it's more like a policeman having a pistol in his hand. He just try to point and shoot, right? And it's every time he just point to shoot, right? James Bond, right? And interval estimator is a bad guy in the James Bond movie, right? He tried to blow up the world, right? Or the terrorist, right? Try to have a nuclear bomb, whatever, right? It's crazy dictator, right? So that's what happened, right? So point estimator is to pinpoint exactly one value. Interval estimator is more than one. It's a bunch of points, more than one. Okay, and of course you would ask which is better, but just different type, right? That same question asked. If I try to catch a robber, should I use the pistol? I use the rocket launcher. I use a bomb, right? It really depends on the purpose, right? So if just want a point, use a point estimator. If you want to be a little bit more precise, then use interval estimator. But probably everyone noticed, right? Tomorrow we have a typhoon, right? Right? Or maybe tonight. No, just by 5 p.m. we have a typhoon number 3, skipping typhoon number 1. Right? Let's see the map, because I think that's easiest to see why you have point estimator, interval estimator, right? Why? Because for teaching, right, should be a little bit more lively, right? Rather than just going through nonsense Say, let's see typhoon satellite probability, right? So let's see some images, I guess. Do we have maybe I should go to observatory, right? Hong Kong Observatory. So that's the best to look for a while. Okay, look at Hong Kong Observatory. Okay. So we should look at the typhoon. Where oh yeah, tropical cyclone. Oh, why it's not there? Forecast probability. Yes. So you can see this is the probability, right? It's called interval estimate, right? They tell you not pinpoint where you are, but pinpoint a bunch of location, right? So you can look at the map here, right? Depending on the color, it tells probability. So this is a interval estimate. Okay, so probably you want to know what is point estimate. Let's see what's point estimate here. Where's the point estimate? Yes, this is point estimate. Okay, you see the line is the point estimate. Okay, the yellow is the interval, right? So interval is usually or very often is in the center of the interval, right? The point estimate. So you usually pop both, right? Not just once, right? Because you want to know the value, but we want to know range of value that likely that high lies, right? So that would be the idea, right? So that is the best, I think, for the best reason why we want to study probability, right? We know how to read this graph, right? But anyway, I hope it makes sense why you would want to know both. Okay, you want to need to know both as well. So now the next part would be, as I said here, this often you will see in the financial forecast, right? In the TV, right? They say what's the price we expect. Then they will say what's the minimum, what's the maximum, right? That's in the daily world, right? You will not say interval, but you will say what is the worst guess you got, what is the best guess you got, what is the medium guess. That is actually point estimate interval, right? So that is the worst case scenario, best case scenario, and the average scenario. Okay. And for point estimator, we will give you three properties, and we will show you sample mean satisfy this nice property, and somewhat we explain why the sample variance need to divide n-1. Okay, it's something that you would rather wonder, right? So then we do divide by n, right? But why n-1? Okay, there's some reason behind that. Okay. So first, there are three property there. First, unbiasedness already. Actually, we said on Thursday, the soccer and not, right? Remember, I don't know, still remember, Cristiano Ronaldo or Messi can kick the ball every time, but me, very bad. I can kick outside 3-point, but on average, I'm as good as them. Oh, you forget about that. No, that's okay. We'll quickly draw it again. So unbiasedness means the following. So here there's a goalpost, okay? And this is your football star, whatever, CR7 or Messi, right? And they're so good. Of course, they're professional. They always get into the goal, right? And this is me, okay? Somewhat handicapped professor, okay? And what I'm going to do is, okay, I'm not good, but on average, I'm good, okay? Although I don't hit inside, but on average, I'm inside, right? So in terms of unbiasedness, we're the same. I mean, I'm same with all the football stars. But of course, not for example. Then, anyways, I'm way off, and this guy are way in, right? So that's why I come to second criteria, which got efficiency. How good is it, right? My one is different from the real one a lot, right? Look at the values. Okay? Distance from the real target is every time is very far away. right? For them, it's almost inside, right? Maybe this, I mean, they are actually something like here, 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 right? They're here, 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 right? So they are much closer, so they're more efficient than that. Okay? So in terms of unbiased, let's say, but the efficiency that. And this is the two. Okay. The last one is slightly a little bit more complicated, okay? Because it requires you the idea of taking the limiting case. Okay. It is essentially saying that if I have large sample size, a large, will I eventually get the goal? That is actually wrong from right. The last number said if I have very big sample size, we will get the population sample. In general, we all want the same thing. Is I have as many sample size as I want, my estimator will reach us to the parameter that we want to test. So that's fine. Okay. At the end of the day, okay. So there can be estimator that is biased but can be consistent. Okay. Because they are different things. And go to infinity, they get cancel out. Bias go to zero. But anyway, we'll talk about that pretty soon. Okay, so don't worry. That is something that we'll talk about. Just I guess we are not that. It's more like theory, but I just introduce it. Then you know why they're good. Don't think we directly ask you. Maybe the side of the quiz. So that you know what are they, because it's important, right? You understand why we have to do this kind of estimation, okay? Especially to explain why the sample variance ID. So an unbiased, as you expect, would be saying if we repeat this measurement many times, on average we get one. Okay. Let me see why this is not well. Okay. If I do an example, okay, I do the calculation, put the theta n is value sample mean. X bar, right? And should be expectation of X bar will be equal to mu. Write that down in case you not fully follow. Okay. The bar means this is the rule, right? This is the way we basically in the sample mean idea is this. If in the sample variance is like this, which will prove this is true, but this is the idea. Okay. What does that mean? It means that if I have one sample, I calculate sample mean, get one sample mean. I collect another sample. I do sample mean, another sample. For sample, similar. Okay. Suppose I do 1,000 samples. 1,000 samples. Average of the sample mean will be population. Same idea for sample. I do one sample, I calculate the sample variance. I do other one. Okay, 1,000 sample variance. Averages of these sample variances should be the population variance. You know this, we actually in the world we never actually do 1,000 samples. Just do one, right? But this is just saying that we have trust in the process. What we're doing, we're right, and potentially someone in the future repeating what we're doing, okay, and it should be able and everyone should discover true. But at least the process that we're right, right? Because at least potentially repeat this is right, right? At least not too far, right? If you're able to repeat, you still get wrong, then it's very bad. So bias is somewhat on average is a good thing, right? But of course, it does not guarantee if you only have one observation will be good. No, not good. But you can imagine because of AI or all the supercomputer, big training, right? You keep learning and this would be good. But that would be the idea. Graphically speaking, it's like this, right? Suppose you want to keep the full eye, which is middle, right? And on average, target means that it can be about on the right bottom or left bottom. On average, you see. It doesn't mean that it didn't get it, but on average, it didn't get it. It's like me. I'm a poor soccer player, right? And I don't hit it. But on average, I hit it. Okay? It's very weak to fight, right? It's not asking you every time. Can be every time I doesn't get it. But on average, I get it. So, that is the idea. Okay. And as we can see, right, it's not very meaningful. Sometimes they compare makes yourself to me, because if we are all unbiased, then right, that's times the indicator. Right? So we want it to be saying that okay, they are more closer to the goal than they do. Right? So we will require us to say an estimator is more efficient if the variance is less, right? So let me give you the example of such. So this, okay? A is closer than B, right? A is closer to the target. When A and B, right, or the average in target, right? So you can't really compare. But you can offer that, right? You can compare if they are closer to the target than other, right? So if I were you, I'll pick A over B, right? Although both of them are good, right? Just like you would want someone to kick the ball, right? You, of course, you want your football famous star than B, right? Although I'm biased, but probably not going to work very well. So this is the two concepts. Lastly, this is what consistency, as I said, is when the sample size gets larger and larger and larger and larger. The one that is different from the target will be probably seen. So that means that you would get it, right? As n increase. Okay, so that's why I look like this. Okay. One is not biased, it's not biased, it's biased. Two, somewhere there is also bias, it's also biased. But when you get more and more data, eventually it's more squeezed inside at the end, the distances between what you get and what the end result, we have zero distance. And it's smaller and smaller and smaller. It may not zero when the number of sample size is finite. But when you get more and more, there will be no difference. Okay. So once we define, we will tell you that sample mean is a. I'm not going to prove, I'll just state the result. Okay. The first is unbiased because we know that already, right? Next part is something. The second one, you want to say, is it efficient? Yes, it's most efficient when you talk about all the linear or weighted mean. Because we learn the mean, you just take 1 over n for each one. Right? But you can weigh different types. And what the proof here said is, don't forget about the proof, but what I say is the simple mean is better than the weighted mean in terms of efficiency. Okay? It's more even. The last one, consistency, followed from last law of last one. So that's why we always talk about sample mean. Right? Sample mean is so, and we really nice to surprise it. Efficient is more or less efficient among some class of answer, and it's always consistent. Okay? So that's why sample is great. Now, second, we'll try to justify why we have n minus 1 not n. And I don't do the proof, but the key part of the proof is because of why you did n minus 1? Because of this guy. If I know the sample, if I know the population mean, I actually do about n. little mu. Because I don't do it, minus the reason if you look at textbook, they call it good reason. Why? Because you calculate this sample variance. You first calculate sample mean, right? You first understand sample mean. That is that if you have n data point here, you calculate sample mean, which means that if I know the first n minus 1 data, but not the last one, the sample mean will already tell us the final score. Right? Suppose you have 10 data points. Okay? Sample mean is some number. I tell the first 9 numbers. You can, and the sample mean, you know the last number. Right? It's adding up the 10 numbers, you go by 10, it's equal to sample mean. Right? So the last number, there's no variation. Because once you fix sample mean at 9 number, last number is fixed. So that's why the freedom. When you calculate variance, if you have to guess the sample mean, then actually you don't have much variance. So one variance less. So we actually divide by this one. Of course, the actual proof would need to look at the math. And I don't advise you to go further this one because I think I waste 4 weeks of my life in the library to figure out why. But I guess now the ChatGPT or AI can keep asking the AI why the X. But I actually remember I do look at every textbook I can find in the library to understand what people feel. Because it's very confusing to be so far. Until now, I don't really get it. Okay? I mean, I understand the math too, but I don't understand the intuition they said. And I try to make it because I'm not super convinced what is meaning of that, but I can tell you this is what I understand. But maybe ChatGPT can tell you better. Because all the textbook seems not to explain it very well. But that's why you divide by n minus 1. Because this is unbiased. Okay? Expectation of the sample value. That is okay. So that is the reason you have to do this. It's the sample version and population variance. And same as what we talk about precocious excuses. Why the sample version and population variance? Why the sample version is so often? It's because of this calculation. You want your thing to, on average, hitting the target, you have to use the ugly formula. Yeah. It's like how we play basketball, right? You can't really aim for the basket, right? You have to, only unless very good, you aim for the basket. The ball. Right? So that's the main idea. You can't really get there by directly going there. You cannot go straight line. Okay, so there's a proof, but I don't want to bother with that. Okay. So here we have standard error of sample mean. The standard deviation of sample mean, right? The sigma square root A. And that means that you have an estimate of standard error of mean will be replaced by sample variance. So this is the one as X bar. Okay, we'll use it a lot of time later. Okay. Now here we talk about a little bit about binary data. And try to tell you what is bias and the point estimate. Because binary data is something that we often see here. Okay. And remember the with binary data, there's nothing new, right? But only the connection between the mean. So we have the sample mean as a sample proportion, right? Mu is pi, okay? And the sample proportion is sample mean, right? So that is nothing new there, right? So that is nothing new. We learned it from the last chapter. The only thing new will be saying that we will show expected P will be pi, right? So that's unbiased because that's nothing new but learning from the previous chapter, right? This is something like we have said already, right? This is the sample mean is unbiased. So when you confine yourself to binary data, still hold. But the next thing is something that I think blows a little bit your mind, because that is slightly, I don't know, but why? This will come to be. We say sigma squared is pi times 1 minus pi. And turn out the one used is p times 1 minus p. Then, okay, you may ask, where's n minus 1? Right? Why suddenly n minus 1 suddenly is here? Why I can use this? Okay. There are two answers to this. One, this is still consistent, but it's biased, right? Because I don't have adjustment of n minus n minus 1, but this is still good. Okay. And you may, okay, should I do this, right? This is the way that I should do the adjustment like this. Okay. Along that line. And this is how that's the version. And one explanation to you is for binary data, n is usually very large. So this adjustment, whether you have or not have, doesn't really matter. And p times 1 p tend to be less. So that really doesn't change the proportion. Here, 1 minus 3 7 C. So that's why in many textbook, okay, that is what we have. Okay, it's biased, but it doesn't really matter. And that's all technical. And but at the end of the day, this is still consistent. Okay? So n go to infinity, that is still going to what we want to get. Okay. So we'll just do this one, find data. Although there's no harm to use n over n minus 1, but I guess we just follow the certain books. If there are some people challenge this thing, I need to use n over n minus 1. Follow different textbook that they actually complain this is not entirely right, but that's okay. I mean, we are not that picky. Okay. So that because they will make our formula easier to use, right? So the sample variant of sample proportion will be p times 0 over n, right? Square root of p times. So that n with all one estimate. One estimate, the data, you want to estimate the mean with the variance, right? And final data, you want the mean and variance. So you get all the fit, right? Because class, you only care about mean and variance, right? Of course. In the first topic, we talked about students' psychosis that actually applied to people. But we are not, we're just skipping those because I guess for a fun problem. Just give you some idea. Okay. Is there any question? Go with 5 minutes earlier, but I guess we should take a break because I don't want to jam you your mind because I think you deserve a rest because I think you guys are super tired. Imagine I'm sick, so I can still talk. You're sitting. So, and of course I get paid. But, so it's slightly different. So that's a break of 15 minutes. As usual, we resume at 5:35. In the meantime, I would recommend you to play the ball because I know how fast I'm going. Thank you. So battery is gone. So luckily we're back. Surprising it's gone when we have break, but for some reason. I hope you good rest. So take care. Don't like me. Get sick. Was not doing anything during the weekend, but just sleeping on the sofa. But hopefully you're good. Good luck with your health. Yeah. So it's weather changing, so make sure that you have enough clothing, a jacket or whatever. So now my back have a jacket, so make sure that you don't get cold. Do you like Thai food? Yeah, I do. When I was a kid, actually, I really Thai food because when Thai food is there, then no more hot weather. But my brother, who was more outdoor oriented, he likes. But I'm an indoor guy, so I just we're happy, right? When you're outdoor guy, you can't go out very sad. But when indoor guy, then you have this. Then at the time you don't have much aircon. Then this is very nice, right? It's raining and the except typhoon number 10, but 8 is okay, right? 10 is a little bit crazy, but 8 is good. Voo, voo, voo. The window is like it's very fun. But of course, not good when you number 9 or 10, the window is like shaking a lot of time. Good. Weather, yes, cloudy, not rainy, but as you said, as the class conclude, probably you have typhoon number 3 already. So hopefully everyone will stay dry and safe. Yeah, that's what we do. The point estimator is very important. So we learn how to estimate mean and variance by sample mean and sample variance. And they have nice property, okay? Unbiased, the main purpose. The sample variance binary data, yes. Unbiasedness, that's good. Okay, the speed is okay. You can also follow. Not too bad. Whoa. So now we have basically everyone is very tired. Usually we have some number here, but now today it's gone, right? So usually 5, well, now you have a 90, almost 90% of you strongly agree you are very tired, okay? I can see that. But so that's why I slow down a little bit. Hopefully still you can absorb the material. But luckily this week is more like this class, the first half of the class more like theory. So just some understanding without math. So hope you are still okay. Yes, the self quiz supposed to finish. By finish, I mean you submit. So you just click and submit that. I think that's fine, right? I think you just spend no more than 1 second and you do it, right? I'm not checking whether you have done it or what. I mean, as you click, you're done, right? Because to be sure, I think there at least 1/3 of students probably don't even bother to click. So you just click, you're done. So I don't see anyone will complain, right? I mean, just click. I mean, so I'm not checking whether you do it. Say how much time you do it doesn't matter. The answer is there. So if you get it wrong, doesn't matter because I'm not checking at all. So just make sure that you know what's going on here. Okay. And some of the material may be more advanced, maybe less advanced, but just let you know what's going on. Okay. So let's because this is the first time I introduce a self-checking quiz. Because last year I keep having requests from a student. I need more exercise. I need more exercise. Where can I find those? Okay. Now I give you some, so you don't have to ask me again, in case you want to do it. If you want to do it, just don't do it, right? Because you just don't even do just click and submit. So just 2 more click, right? So there's not something you create a lot of trouble for you. I hope that's okay. Yeah, it's really cool. So I guess time to hike. I think CHK is a good campus. You can hike around. You can skip the bus, right? When getting the winter. That's a good thing about CHK because you talk to any place in the world, all the good school, they have very flat land. That's very boring, to be honest, right? But you now have go up and down. It's always very wonderful. I always talk to people. They come here amazed by our campus. I mean, probably you would like to have a flat land, but I think we have much more interesting landscape. You can go up and down. It's more fun. right? I mean only if you don't appreciate that, but when you actually try to go to the place where everything is flat, we appreciate we are very good. Just like weather. I mean, I was in Singapore for 7 to 8 years, then the weather is same every day. So not say good or bad, but it's like monotonous, very boring, right? Here, Hong Kong is like kind of 4 seasons. So you do have some variation. Some variance is good, right? If you don't have variance, then like life is a little bit same every day. But it's okay if you like the same thing. It's okay. But I guess I more enjoy the more exciting part of the life. So now we have the point estimator, and as we said, we also want interval estimator. Right? You tell us something, just like remember the opening example about the satellite image on the typhoon map. We do have a point estimate, but we also have the interval estimate, right? So now we are going to tell you how to get this estimate. So of course, we can't tell you how the observatory can do it. If we do, then become science class. But we do tell you that what is the rationale behind it, what is the principle they're working on. It will not be too much different from what we are doing. Okay? But that's more complicated model. So what we will do is we will make some assumption to make an interval estimate. Okay? For point estimate, don't make an assumption. To make interval estimate, we need to make some assumption to make our guess right. So we need to know the distribution is following normal, or we have a large sample size, so central limit will apply. So that means the sample mean follow a bell curve. But without a bell curve, we can't say too much. So for the interval estimate, we also limit ourselves to sample mean only. Sample variance is beyond the scope of our class. So look at interval estimate for sample mean. Okay, and to do so, either we assume the underlying is a bell curve, or we use central limit theorem to say it's a bell curve. Okay, one or the other. So if you don't do that, then you cannot do interval estimate. You have to make some assumption, and because you see why we have to do that. So that is a little bit tricky here. I have to be slowed down because the meaning of interval estimate have to be precisely described. So what we want is to have what they mean by interval estimator is starting from the sample mean point estimate x bar. We go left and right by some distance, same distance, such that there will be high probability that the sample mean include the population mean. Okay, let me say it again. It's very tricky. The sample mean is a random variable. Okay, I guess that. Once I guess that, and I add a distance to the left, distance to the right. Okay, I want this interval, which will also be a random variable. Okay, have high probability include the population mean. Okay, so do note that the public statement is on the random interval you're talking about. Okay, it's not saying the population mean has high probability within this interval. That's different because the sample mean is a fixed number. The population mean is a fixed number. It's not there's no probability whether this get in or not. Rather, the random variable is your interval, right? Depending on data you get. So that one will include or not include. Okay, a high probability or less probability before you do the data. Okay, before you have data, you can say probability, right? But after you get data, you have a number, you cannot say probability, right? Whether it's in or out, right? It's not probability. So that's why what we later will see, we'll call this confidence rather than probability. That's why you see confidence interval, not probability interval. Okay. Before you do let me repeat because it's very tricky. Okay. First, it is not the population mean fall into this interval or not. Okay, there's nothing to say that because that is a fixed number. There's no probability of that. Second is the interval, which is random variable. it will include or not include with high or low probability. Okay? This estimator has, but once you do the estimate, once you have the number, it's no longer probability. Okay, we will say whether we have high confidence it is in or not. The confidence is what? It's just saying that if supposed to repeat this process many times, a lot of time, a lot of them will include. So that would as a confidence. Okay, it's supposed to repeat this many times. Many of them should include the true mu, but we don't reach one. Okay, just that is the confidence, but we only do one. So that is why we believe the system is right. Okay, we believe algorithm, the method we do is correct. So that is very tricky. Okay, of course, if you don't do that, doesn't really matter, right? Because, but I want to let you know this is very important because many textbooks would spend a lot of time explaining why we call confidence interval. Later you will see, but not probability interval. It's not probability. Okay, it's confidence because in classical probability, right, only things in random variable randomness can assign probability, right? The population mean is not a random variable. You can't say probability to that. Okay, and once you collect data, there's no probability, so you cannot say that as well. So it's the process before you do it, you can assign probability. Once the data, you only say confidence. Okay? Of course, if you are more than probability, you are Bayesian, you cannot say probability, but it's beyond the scope. You are still within the classical probability world, where you can only assign probability to something that hasn't happened yet, right? Something happened, you can't say probability, right? So that's the idea, okay? But let's see what we're doing. So the statement about I have X bar, I go left and right, have high probability include mu, it's like this funny formula here, okay? So what it said is I have X bar here, okay? I have X bar minus M, okay? X bar plus M, okay? I want this interval, okay, have high probability. By high means 90%, 95%, or 99%, that's usual. That contain the mu, okay? I don't know mu is where, but I want it have high probability that we will include the mu, okay? Mu is somewhere, okay? Alpha is usually 0.1, 0.5, or 0.01. Okay? And classically, alpha is 0.05. That is something that we would do in most applications. 95% is something that we want. Okay, and mu so, which is something probably the only proof we do in this class. Right before we don't do any proof, but I think we should do this one. But don't worry, the proof is just 3 lines. Okay, it's not something. Don't worry, it's not something. Turn out this M, okay, with the size of this, is nothing new, but just the standard error of the mean times this number. Okay, we will see what this number is, but this is the result. Okay, we will tell you what it is. Okay, don't worry about that. It will be clear very soon. Is that okay? What do you know what we're doing? Okay, what we're doing is instead of X bar only, we want X bar go left and go right. Okay, under normal, how far you can go, which come from the Z. This one we will clear more later. Come from the Z table, and you go left and right. Okay? And if you want alpha is 5%, okay, then this Z alpha 2 is close to 2. Okay, it's close to 2. Okay, it's just basically this coming from the 65, 95, 99 rule. So this is coming from that. You want 99, right? That will be 2.16, something like that. Okay, anyway, we will see how to get the number. But let's see how we do it, okay? So that is the definition. We will talk about that. But before we said this is called confidence interval, which I will tell you why it's confidence, because there's no probability. Okay, so that's why we give some name there, confidence. And that is called the length, left and right, is called margin error. Okay, I think I said already, right? If you remember, this is x bar, right? This is x bar minus me, if you want, right? This is x bar plus me. Okay? This is margin error. And the width is this one. This is width, right? That's 2me because you go left by 1me, go right by 1me, right? And this is the lower one, right? So this is the LCL, lower confidence limit. This is UCL. So this is what this graph is about, right? Nothing new here, just different definition, okay? But I hope we will try to give you reason why this is right. Is it okay for this one? This definition. So nothing to digest, but just you know it, okay? Just you know it. But now we're going to explain a little bit why this is true, okay? Although I guess you really hate the proof, but unfortunately I have to work a little bit of the proof, okay? So first, we say because central limit theorem or normality assumption, we have this, right? We have mu sigma square over n, right? So this is something we know, and this is the bell curve. Right? So this is sigma alpha. Okay, so this is what we have. Is that okay? This is the assumption. This is the starting point. The sample mean for a bell curve. Okay, nothing to understand. This is coming from central limit theorem. Or you assume the underlying x, every observation is normal. The average is not normal. Okay, so this is the starting point. Now, what we want is we don't know mu, right? So we really want, when we draw a sample mean, maybe somewhere here, right? We'll draw somewhere here. Then we won't go left by m and go right by m, right? And this interval will include mu, right? Is that clear? So because the data you get is somewhere here, right? It end up maybe the sample mean is here, right? This is number you get. Then you want to go left by m and go right by m. And you want this interval with length of 2m or 2me will include the true mu. Okay? That's what we want. So how do we find that? What is the m there? Okay, how do we find m there, right? Because you know what kind of sample mean is the bell curve, right? So it's more likely to center than outside. What should be the m? What should be the m there? Okay, we want this interval have high probability that include this, right? That means that suppose alpha is like 0.05, okay, 5%. Means what? It's suppose I construct 100 of them, 95 of them should have the mu, right? If I draw. But how can we do that? How can we do that? Think about this. How can we do that? Okay. How can we do that? So the idea of this is to think a little bit reverse. Okay, a little bit reverse. Okay. If I construct interval, the sample go left by m and go right by m, right? Every time I have the same m, right? So we can reverse the idea. You think about the following. Instead of this, you can think about this way. Mu, I go left by m, I go right by m. And if my data is within this range, then if I construct backward, then I'll include the mu. Right? Let me say it. If your data is around here, right? Mu plus m, mu minus m, right? And suppose you get the data here, right? Get it here. You construct m, it will include, right? Right? If you outside, you're not, right? So that means that I go mu by left by m, go right by m, right? Then I'm done, right? What I need is the probability of this is just 1 minus alpha, high probability, 95%, right? Then 95% means what? This is alpha over 2. This is alpha over 2, right? So if it's 95, say 95.95. This is 0.025. This is 0.025. Okay? So that's why this number, of course, I should have said so. This is in the textbook. Many often they will call Z alpha over 2. Okay? Is the because you convert it to normal, right? Because you can always, this number, this is Z over, this number will be Z sigma over root n, right? Because you convert it to Z, this becomes 0. So this is Z alpha over 2, right? So this is the alpha over 2, right? So that, because you convert this to back, you just multiply by the SD, right? SD is just sigma over. Okay? So that's why M is what? M is just this guy. So this is the proof. Of course, if you don't get it, it's okay. As I said, it's in the black one. I want to go through that because that is the proof behind the 2-page slides. Okay? But in the black one means that if you don't get it, it's okay. No panic. Just remember the formula, then you're done. No way I will ask you to prove this thing. But let me explain it once again because I want you to know, because that would be better to understand what's going on. The goal is, let me do it again, right? Is we know the bell curve. It's bell curve, right? So you will draw a sample mean, then it will be along the bell shape, right? More likely to be centered than other way, right? Following the bell. And when you draw it, you want to go left by m, go right by m, right? And you want many of those would include the mu, right? But it just say same as the mu, you go left to right by m, okay? And the probability of this is large enough, the same statement, right? Because when most of the data is here, right? So you go left by m and right by m, it's the same as the data, you go left and right by m, okay? And what is this number? Convert to z is just C alpha over 2, and it's multiplied by SD, then go back to the standard. Okay? So if you get it, it's good. You don't get it, it's okay. Because I think when I was a student, I don't get it the first time. I just copy the formula and just apply it. Okay. After a while, you will see why this is true. Because you construct this many, many times, same as you construct from the center. Right? But the idea is you basically thinking about constructing many, many common intervals. Right? And many of them would include or not include. Okay. That is same as finding the probability here. Okay. But as I said, this is something that if you don't get it, it's okay. So don't feel too stressful because this day, many of us have many things to do, right? Try not to understand everything. That's very important, especially for those who want to go to graduate study or go to do a master program. Is you have or go to the real world. Is you have to live with problems. As a primary school or secondary student, you always want to solve the problem. You leave no doubt in your head. But actually, probably now increasing your second year, third year student, you notice that there's something you don't understand. right? So you just live with the problem. There's something in your head doesn't, not everything you can make it clear. If you try to make everything clear, then you run out of your life, right? So have to forget about things, right? Just like in the future, when you get married, you have to do the same, right? Whatever your partner is, don't try to make clear everything, right? Something you have to live in uncertain, right? Have some probability is better, rather than knowing the real truth, right? Probably you can't accept the truth, right? So better not to know everything, right? Don't ask the background. You have to clear everything from the beginning of his life or her life. It's not going to work. So same idea here, right? If you don't understand, it's okay. Don't have to understand, right? Just the only thing to understand for me is okay. I know this is the way to come up with the interval estimator. Okay, this is the formula, and I'll tell you how to apply. You look at the green, you apply in the exam. That's fine. When you don't understand, it's okay, but because when you see it again, then you may want to know it, right? When you see it again, you don't feel comfortable, then you look at it again. Okay? Maybe the slide will be coming back to you, and then you want to know again, right? So I hope at least the formula is here. So let's see this example. The most important is this slide, right? You want to put in practice. As you will see the assignment as well. But don't worry, the assignment will not be released until we're done with hypothesis. So, probably we have done this set of slides with some assignment. So the population SD is 4. And the sample mean, I don't know, right? Sample mean is 3. Okay. The sample size is 64. So I want to know the interval estimate. Okay. First, I know my point estimate. My point estimate will be 3. That's done. Okay. Now interval estimate. How can we do that? You just need to remember the formula. The formula is like this: x bar plus minus z alpha over 2 sigma over root n. Okay. That's it. The formula from the green or purple box. Okay. The formula. Let's apply. X bar is 3. So this is 3. Let me use the color, right? 3. Okay. N is 64. So 64. So this is 4. Only thing to know this guy. This guy is what? This guy is a tail probability. So you'll be doing this. Z is 0. Use other color to make sure that you see what's going on. This is alpha over 2, right? Y over 2 because you want this center is 1 minus alpha, right? And alpha is 5%, right? So alpha over 2 is 2.5%, right? So the right hand side 2.5, the left hand side is 97.5, right? And I want probability go back to the number. So I used norm S dot inverse. Okay. So what I'm going to do, how to get this number? Actually, it's 1.96, but this number, come on, what? Is norm dot S dot inverse. Remember, this is what? 97.5. 0.975. I think that's it. Let me check. I think that's it. So that's why this is 0.975, right? Because 95 in the center, two sides is add up to 5%, right? So then that means that up to that point is 0.975. So that's why you got 1.96. So Sorry, it's gone. So let me write it down again. Sorry. So it's X bar plus minus this guy. All right. So this is 3, and this is 4, and this is 4. And as shown already, alpha over 2 is 1.96. So just you put all the number there, then you're done. Okay. So your guess here would be 3 would be your main guess. And you could say it's between 2 and 4, more or less. Between 2 and 4. You guess 2. And sorry, you guess 3, then you say the worst case is like 2, the best case is 4. Right? So I don't tell you what it is, but this is what you get, right? You tell. On average it's 3, the worst case is 2, the best case is 4. Right? Best and worst depend on what the situation, but the lowest and the highest, right? Is that okay? So I hope that would help you to see what we're doing. Is that okay? So here is what I said already. The interpretation of the confidence interval is not about probability, right? Because once you have the data, you've got a number, and there's not random variable there anymore. And the true population mean is also a number, not a random variable. So nothing is random when you after collect data. So that's why we say probability is, we like the probability of the process, the probability of the estimator, not the estimate. We get a number as an estimate. So that's why in this literature, in the textbook, they have to distinguish what's estimator and estimate. Estimator is a probability, right? Estimate, you have already covered confidence. Right? So the confidence interval. I don't think I need to repeat that because I think I already talked about this many times, but it basically can be summarized by this diagram. Okay? Here, I show you different cases. Let's look at the very first above, right? You may end up in this number with the sample mean, right? And when you construct the interval, go left by right, you will include the mean, right? In the second case, if you construct, you go left and right is there, right? But if you're outside the two regions, then of course you will not include, right? So basically, this is the idea. Okay. So, but you don't know which one is the case, right? Because you never know which, even if you have 100 confidence interval, you only know 95 of them include the true population mean, but you don't know which 5. So we don't know which 95 is yes, which 5 is not, right? But this is what you have, right? So you don't have you have no idea, but at least that lot of them will include. So that is the idea. So I hope explain the idea. It's very subtle, right? But as I said, we are not stat class, so I'm not trying to ask you this subtle thing, but rather I ask you to operationalize this thing. Okay? The subtle thing is just for your minds only. Okay, you will not be asked this type of question, but I have to teach you this. Otherwise, there's no point coming to class. Right? Just remember the green thing and remember the purple thing, then go home, right? And do the assignment. But you're going to come to this class, you want to learn a little bit more about the background, right? Give you some basic information as well. So you may probably have this question. As last class, we emphasized, without sigma square, how can we do this? Right? So far, we have write this thing, right? It's like we go left and right by z's alpha over 2, sigma over root n, right? By sample mean, but in many cases, we may not show sigma square, right? No population values. Sometimes we do know because the high confidence we can guess it, right? But many times we don't. Okay. So how can we do that? So here's the T come to save our life. Okay, but of course, there's some cost of saving a life is we have to assume normal. We can't use central limit theorem to justify our thing. We have to use normal assumption, normality. Okay. And as I said, if you don't like normal, you need to have more advanced technique. Okay. So we just in our class, same as many other the graduate class as well. So normality is assumed. Okay. If you want to do away with that, we need to use other technique. But let's assume this is true. And we already said, if that's the case, this guy is t minus 1. Right? This is what? This is a bell, right? But a bell that is a little bit fatter, right? So that's good. Everything is staying the same, but just at some causes. But we know the bell, and but more problematic is the bell has many different. One, the bell depends on the sample size, right? The larger the sample is more like the normal bell, right? The smaller the sample size, then it will become a fatter bell, right? So that's the only thing we need to know, the sensitivity distribution, right? So the same logic will apply, okay? To tell you the same thing, if you replace this no longer sigma, you S, and you only check the T table, okay? And T table, you pick up particular T table to check, is M minus 1, right? Sample size minus 1. That's the only thing, right? Same thing, same logic, okay? Not same, just a T, and then also left and right, same idea. So behind why this is true, but I'm not going to tell you. I'll repeat the same argument, right? Same T. Now let us get ourselves to the definition. Okay, this is, as I said, the purple thing is you should bring this to your exam theater, right? But remember, there's no limit on cheat sheet, so you can bring as many as you want, as long as you can write, or as long as you can type, as long as you conserve the world, right? How many papers you want, but other than that, there's no limit, right? So that is the formula. Okay, T minus 1 over 2 S over root n, okay? And seems to be nothing new, right? But let's see the example, I guess, that would help us to give you the idea that how can you guess number, okay? Let's see the for example. Maybe we're boring example, but you can imagine there's a lot of use cases, right? Because estimating sample mean is something useful in many business situations. But let's see the example here. First, we have to assume normality. Otherwise, we can't do anything with unknown population variance. That's something that we have to assume, okay? And what we have is the sample size is 20, sample mean is 3, standard deviation is 12, okay? So just, we want to find 95% confidence interval. So without further ado, just do this, right? Just copy the formula from the last slide, right? So just try to fill in, right, the formula, right? Nothing new there. Just formula from last slide. Just figure out which number to be put in. Then you're done, right? So I say you can see this class is not very difficult, right? Just this like primary school or secondary school, right? Equation, you know which should apply. Put in the number, count the number, done, right? So already you know sample mean is 3, so this is 3. All right? The sample mean is sample mean is 12. Sample mean is 12. This is 12. N is 20. This is 20. Only thing is this guy. Right? Only thing this guy. But what's this guy? This guy, the bell curve. Nothing but a bell, but with a fatter tail. Okay? Bell. So Tn minus 1. Send that 0 here. Right? Not really a bell, but let's do it better. Right? We want this to be, this area is 1 minus alpha. Is here means 95% or 95. Right? We have a high probability that it's within the here. Right? Because that's why how we construct our interval. And if center is 25, both sides are 2.5%, right? Because 95, what remain is 5 on the both sides. So what is left is 2.5%, right? So this is 2.5% on 0.025. This is on 0.025. Okay. So that means that this to the way back is 0.975. So it's T inward 0.975. And then you tell degree of freedom, M-1, which is 19. Okay. This will give you this number. T inverse 0.975, 19. So let me go to this one. Okay. This is T dot inverse 0.975, 19. Okay. You will see this is 2.1 or 2.09. Okay. So this number come here is what we have, right? Right. So that is 2.09. Right. So once you plug in, then you're done. You can see it's nothing very difficult, right? Just a formula, just apply. I mean, same as accounting, right? You learn accounting, right? Just like it's a rule, you just see this, apply, right? So you will see our way doing statistics is no different from the class you liked, accounting, right? Just the rule, you apply. Okay. Of course, you probably want to understand why, same as accounting, right? So we understand why this rule apply, because this is the rule that tell us with large probability that you do this, okay? Not out of 100 of them, if you 100 of them, 95 of them will include the true mean, okay? We don't know which one, okay? But do know that we only just do one, but we have the confidence in the process. So we only even do one, then I think that is good enough, okay? Same as the typhoon, right? What do you mean by 90% that the typhoon is here, right? Means that you have hundreds multi-universe, 90 of them, 95 of them is in, but you only have one universe, right? So you don't never know. But that is the same idea here. Is that okay? And you don't notice that the margin of error is very large, right? It's like 5, right? And you can go to negative as well. So you can see when the n is large enough, you don't have that problem. Okay? When n is very large, then this problem will solve. Is that a question? So now you learn something very important already. You learn how the observatory come up with that, right? Of course, they have a super complicated model, right? But they're the same, right? 90% of them include. There's no different from what we're doing. So you understand what's the meaning of probability in terms of the observatory, right? It's just like, suppose they construct many kind of this, 90% include that thing. Okay, hopefully that, I guess that will make sense to you. Okay. If they no, then we go to the next set of slide. It's talk about proportion. Okay. So there's nothing new there, but except that, as I said in the beginning, you don't really rely on T. Okay. We can use normal. So that's a good thing about binary data is you don't have to assume normality. Okay. Because what's meaning of normality here? Because 0 and 1, right? Your population is either they like the product or they don't like the product, right? There's no need to assume normality because normality means nothing here, right? And the formula is like this. This is the X bar, right? There's nothing new, right? It's X bar. This is X bar, right? And this guy is sigma square, right? So that's why sigma square over n, right? Square root. So the same as this guy, right? Because P times 1 is P is sigma square, right? So that's a formula there. Okay, no need to explain further, right? Because it's normal. Give an example because I think example tells you how to apply it. After the example, we're done. Okay, we'll spare you if you end 1 minute earlier. Okay, because I overrun 1 minute last time. So we try to finish 1 minute earlier. So the formula, again, is just copy and paste, right? Just P plus minus Z alpha over 2, P1 minus P over N square root, right? So this formula. What I do, just copy each thing there, right? And nothing deep, okay? P already tell you 25.25, right? So P is 0.25. The question tell you the sample proportion is 0.25. So maybe you're asking how many people like to go to morning class, right? 0.25, right? And N is 64. You just put here, 64 here. 0.25, 0.25. What left is this guy. This guy you know how to find. In case you don't, I just repeat again. Z is here, 0 is here. You want 1 minus alpha here, right? Alpha is 5%. So you want to do is 1.96 come from this formula again. Is norm S inverse 0.975. Okay? So once you plug in all the number, you can tell the proportion, right? So that is very convenient, right? Because you know, beside the sample proportion is a guess. Okay, you get is 25%. But if you more be careful, it can be as low as 15, as high as 35. So of course, you want to reduce this range. Okay. In the next class, we'll tell you that if I tell you, in worst case, I tell you the margin of error, I tell you how many samples to get. Okay. Here, I tell you what the sample size. I tell you the answer, you tell me the interval. But let's reverse the case. I have my desired accuracy. I want to decide how large is this, because that is how desirable is it, because I want this as small as possible, right? This maybe 0.1 is how much error I accept. Then it will tell us how much sample we got, right? Because we learned that when n go to infinity, this interval will shrink to 0, must be, because that is called law of large number, right? When n go to infinity. So that's why we want to shrink this as small as possible, okay? And when n is bigger, this shrinks. And then we tell you next class, you give me the size of this, I will tell you how much sample size we want to get. Just reverse the formula, don't worry. It's very simple. So, as promised, 1 minute earlier, so I will see you on Wednesday. Remember, your assignment is still on Wednesday midnight. So before Friday, okay? Before Friday, okay? So stay around, answer the question you may have, but that will be today.